there are moments when the universe seems to whisper secrets to us. The last week of September 2025 was one such cosmic whisper. Two distant stars exploded, flooding our celestial neighborhood with high-energy radiation. Days later, Comet SWAN suddenly ignited, stretching its tail across great swaths of sky. Then the sun itself erupted, launching a coronal mass ejection in precisely the direction and timing that defy mere chance. But all this is merely the prelude. Hidden behind the sun's glare, 3I Atlas races toward Mars as October 24 approaches, creating a convergence of electromagnetic forces that could either confirm the boldest theories in plasma physics or reveal the breathtaking power of cosmic coincidence. The next few weeks may show whether we're witnessing choreography or chaos in the electromagnetic networks that bind our solar system. Join me tonight as we delve into the improbable odds of what's happening out there, and above all, don't miss what comes next, because the universe rarely offers such a clear test of its deepest mysteries. Part 1. When the Sky Exploded. 3 times, September 26, 2025. Year 843. UT that morning. The cosmos delivered a 1-2-3 punch that ought to make astronomers question everything they thought they knew about randomness. First came 2 stellar explosions, Nova V7994 Sagittari and Nova V935 Centauri, each blasting our solar neighborhood with intense radiation. Then, almost as if in response to some cosmic signal we cannot yet decode, Comet C2025 R2 SWAN erupted in brightness. Its magnitude shot from around 6.5 to 5.7 within mere hours, and its tail stretched across 2 tau degrans of sky, equivalent to 5 full moon diameters. But the universe wasn't done yet. 48 hours later, on September 28 at 0843 UTC, the Sun's active region 4232 unleashed an M6.4 solar flare, the most powerful eruption the Sun had produced in 3 months. The timing was eerily precise, and the direction aimed straight at the orbital plane through which SWAN was traveling. Ordinary scientific caution would dismiss all this as coincidence. Random events clustering together because, well, that's what random events do. The human brain, after all, is a pattern-seeking machine that can detect conspiracy in a bowl of alphabet soup. But sometimes, patterns emerge so stark they force even the skeptics to pause and wonder if we're witnessing something far more than mere chance. Consider the players in this cosmic opera. Comet SWAN had already passed perihelion on September 12th, surviving its closest approach to the Sun, and was now traveling toward Earth. By October 2021, it would reach its closest approach, about 0.2606 astronomical units, 24 million miles. That's close enough for SWAN to become one of the brightest objects in our autumn sky. I-Your Atlas lurks behind the Sun's glare, nearly invisible from Earth. Discovered just this past July by the Atlas survey in Chile, this interstellar visitor is following a hyperbolic trajectory that brings it inbound toward Mars' orbit. Its perihelion is expected around October 30th, just inside Mars's path. The geometry is almost too perfect. Both SWAN and Atlas travel near the ecliptic plane. Both lie in the same turbulent layers of the heliospheric current sheet, the boundary where the Sun's magnetic polarity flips, and both are reaching intense activity within days of one another, just as solar cycle 25 appears to ramp upward. Even more remarkable, the new moon on October 20th will bring the darkest possible skies for observers, coinciding nearly precisely with SWAN's closest approach to Earth. It feels as though the cosmos has reserved front-row seats for what's about to unfold. Mainstream space agencies remain cautious. No confirmed causal links exist between stellar explosions, comet outbursts, and solar activity. Space agencies and geological surveys emphasize that space weather has not been demonstrated to influence earthquakes or planetary systems in any proven way. These are the guardrails of accepted science, and we dismiss them at our peril. Yet something in the timing feels orchestrated. The sequence suggests we might be witnessing energy cascading from one system to another through pathways we have only begun to theorize. Could nova radiation trigger volatile release in a comet? Could a comet's outgassing disturb the local electromagnetic medium enough to incite solar instabilities? Could the Sun's reaction ripple outward and affect planetary systems? The questions multiply faster than the answers. But here's what we do know. If this is choreography rather than pure chance, The downbeat lands around October 21st. The new moon will darken our skies just as SWAN reaches its closest approach, just as 3I Borealis lurks behind the Sun, nearing its own peak in solar heating. The direction of that coronal mass ejection matters more than you might imagine. What we accept as evidence for feedback loops between comets and our star must be defined carefully, because what we may observe from October 19th through 26 could mark a crescendo rather than a lull in cosmic activity. The stage is set. The players are in position. Somewhere in the mathematics of orbital mechanics and plasma physics lies the answer. Are we witnessing the most elaborate coincidence in recent astronomy, or the first unambiguous evidence that our solar system operates as a more interconnected, electrically coupled machine than we ever imagined? The curtain rises in just 24 days. September 26th began like any other day for comet observers. SWAN had been behaving predictably since its discovery, following the gentle brightness curve expected of a comet 2 weeks past perihelion. Then in the span of just a few hours, everything changed. The first reports arrived from Southern Hemisphere observers around 08:00 UTC. SWAN's coma had suddenly blazed to life, jumping from magnitude 6.5 to an estimated 5.7, bright enough to become visible to the naked eye under moderately dark skies. But brightness tells only half the story. The comet's tail, previously a modest smudge requiring a telescope or binoculars, had stretched into a magnificent streamer spanning 102 gurus of sky. To put that in perspective, hold your hand out at arm's length and spread your fingers. The distance from thumb to pinky covers roughly 20 degrees of sky. SWAN's tail now occupied more than an eighth of that span. A ghostly river of ionized gas and dust, it became easily visible even with modest optical equipment. This was not SWAN's first outburst, nor would it likely be its last. Comets are intrinsically unstable objects, especially when loaded with volatile materials and exposed to the intense radiation environment of the inner solar system. Made of primordial ices and rocks dating back some 4 billion years, comets carry within their nuclei preserved chemistry from the early solar nebula. When solar heating reaches fresh reservoirs of carbon monoxide, carbon dioxide, or other hypervolatile compounds, powerful sublimation can trigger explosive outgassing events. On September 26th, SWAN's orbital location made it especially interesting. Having passed perihelion on September 12th at approximately 1.37 astronomical units from the Sun, closer than Mars but not yet reaching Earth's orbit, it was still receiving substantial solar heating. More importantly, its trajectory kept it traveling close to the ecliptic plane, the imaginary disk along which most planetary orbits lie, a region where the Sun's magnetic field forms its most complex structures. This is where physics becomes intriguing. The ecliptic region is home to the heliospheric current sheet, the vast rippling boundary layer where the Sun's magnetic field flips polarity. Picture a ballerina's skirt, spinning and undulating outward from the Sun at nearly 2 million mph. Embedded within that current sheet are magnetic discontinuities, shock fronts, and zones of enhanced particle density, all of which can interact dramatically with objects that generate their own plasma environment. Comets, it turns out, are surprisingly effective plasma generators. As solar radiation heats their nuclei, volatile gases are driven off and become ionized by ultraviolet light and the solar wind. The result? A complex electrically active coma that can extend millions of miles from the nucleus, well beyond the nucleus itself, allowing interactions with structures in the solar wind before the nucleus even approaches them. What makes cometary plasma especially interesting is its dust content. Unlike the relatively clean plasma environments around planets, a comet's plasma is mixed with dust grains, particles of rock, metal, and organic compounds. This creates what plasma physicists call a dusty plasma, a quasi-fourth state of matter. In dusty plasmas, charged dust grains significantly alter how ions and electrons behave. The response to external forces becomes non-linear. The system can generate its own electric fields and sometimes act in ways that defy straightforward magnetohydrodynamics. When SWAN erupted on the 26th, it was not merely getting brighter. It was transforming from a relatively simple gas and dust cloud into an active plasma environment capable of complex interactions with the solar wind. The sudden increase in mass loading, The addition of new material into the solar wind flow could, in theory, create localized disturbances that propagate both upstream toward the Sun and downstream toward the outer solar system. The observational evidence for SWAN's transformation was unmistakable. Photographs before and after the outburst showed not only increased brightness, but morphological changes in the tail. The ion tail, that blue-white streamer of charged particles, became more structured and pronounced. Dust lanes in the coma appeared more defined. Most revealingly, the tail's position angle shifted slightly, indicating that new gas and dust were being expelled from different regions of the nucleus. For amateur astronomers in the southern hemisphere, SWAN's outburst was a spectacular surprise. Because the comet's declination was low in the southern sky, it was difficult to see from the northern latitudes. But observers in South America, Southern Africa, and Australia found themselves with front-row seats to a cosmic light show. Images flooded social media and astronomy forums, capturing the comet's rapid evolution in near real time. But SWAN's awakening raises uncomfortable questions. Comet outbursts are not rare. For example, Comet Hale-Bopp produced dozens during its 1997 apparition, and Comet Lovejoy's 2011 sun-grazing passage triggered dramatic eruptions. What makes SWAN's timing noteworthy is its proximity to other high-energy events in the solar system. The nova explosions that occurred just days earlier represent some of the most energetic phenomena in our galaxy. When a white dwarf accretes enough material from a companion to trigger a thermonuclear runaway, the resulting nova can briefly outshine an entire galaxy. The high-energy photons, gamma rays, X-rays, produced in such events travel at light speed and can reach Earth and the inner solar system within days or weeks. Could such radiation have contributed to SWAN's outburst? The energy flux from distant novae at Earth's distance is negligible compared to solar energy. Yet comets are exquisitely sensitive to even small changes in their thermal environment. A slight uptick in heating might prompt sublimation of previously dormant volatile layers, especially in a nucleus with reservoirs of hypervolatile compounds like carbon, monoxide, or nitrogen. The physics remains speculative, but the timing is undeniably intriguing. Two nova events saturate the inner solar system with high-energy radiation. Days later, a comet suddenly erupts in brightness and plasma activity. And then, as though responding to an invisible cue, the Sun itself erupts with its strongest flare in months. Coincidence, perhaps? But as we will see, the Sun's reaction to SWAN's awakening suggests that something far more complex may be unfolding in the electromagnetic soup around our star. These structures spiral outward from the Sun like water from a rotating garden sprinkler, creating the interplanetary magnetic field that fills the space between worlds. Traveling at roughly 30 km in its orbit, SWAN faced a potential direct hit from the approaching CME. On September 28th, the comet was located about 40 million miles from the Sun, well within the distance over which CMEs can maintain coherence and magnetic strength. If both timing and geometry aligned, the shock front of the eruption might reach SWAN's position in 2 to 3 days. This sort of scenario has played out before, with spectacular results. In 2007, Comet Encke offered astronomers a natural experiment. A CME struck its ion tail directly, and the stereo spacecraft captured the interaction in detail. The tail was literally severed from the nucleus, carried off by the solar wind, even while new gas continued to flow from the nucleus and gradually rebuild the tail. Space Math. NASA Scientific Visualization Studio +2. The physics behind tail disconnections underscores the close connection between comets and the solar wind. A comet's ion tail forms when solar ultraviolet light ionizes gases in the coma, creating charged particles that become coupled to the Sun's magnetic field. These ions are then accelerated away from the nucleus by the solar wind, forming the straight, blue-white streamer that can stretch millions of miles. Wikipedia +2 Nature +2. When a CME collides with this delicate structure, multiple things can happen. If the CME carries a strong southward-pointing magnetic field opposite in orientation to the magnetic field in the comet's tail, magnetic reconnection can occur. This process reconfigures magnetic field lines and severs the connection between tail and nucleus, somewhat akin to how auroras arise via reconnection in Earth's magnetosphere. Art exibos 3 AGU Publications alternatively, the CME's ram pressure, the force of high-velocity particles, may overwhelm the tail's magnetic structure, shredding it like wind through smoke. In either case, the tail may disappear within hours, leaving only the nucleus behind, while the comet regenerates a new plasma envelope over time. If SWAN were directly in the path of the September 28 CME, observers on Earth might detect an abrupt change in tail brightness, morphology, or position angle. Seasoned comet watchers always monitor for disconnection events, DEs, during periods of heightened solar activity, since such events offer real-time evidence of invisible electromagnetic forces shaping our solar system. But there's a deeper question: the 48-hour delay between SWAN's outburst and the Sun's eruption is comparable to the range of possible light travel times or signal influence times between comet and Sun. Could SWAN's sudden surge in plasma output and its enhanced mass loading have triggered instabilities in the solar corona? Mainstream heliophysics is mostly skeptical. The Sun comprises 99.86% of the solar system's mass, and the energetic contribution of a single comet is usually negligible in stellar-scale processes. Active region 4232 was likely building magnetic tension independently, and its eruption may have been inevitable. But the precision of timing is striking, and that merits caution. If one were to perform statistical analyses over multiple solar cycles, comparing comet flares and solar eruptions, one might try to assess whether such synchronizations appear more often than chance would allow. The challenge lies in precisely defining meaningful correlation across vast scales of space, time, and energy. One thing we can observe directly is the continued outward propagation of the CME. Models based on solar wind prediction systems suggest the shock front could reach the outer solar system by early October, potentially sweeping through zones where both SWAN and the interstellar visitor 3I Atlas travel. If correct, both objects might experience electromagnetic influence from that same shock. From Earth, the next few days will be critical. If SWAN's tail exhibits a disconnection event, a rapid disappearance or major structural shift, that would strongly hint at direct CME influence. Whether or not the comet reconfigures itself rapidly could help us distinguish whether we are seeing a routine interaction or something deeper, a clue to an electromagnetic coupling between comets, solar output, and the broader interplanetary medium. As September transitions to October, the stage is set for a possible celestial collision, one that might illuminate hidden networks of energy and information that bind our solar system. The big question: are we ready to detect the signals when they arrive? Even the most powerful nova explosion, when viewed from thousands of light-years away, delivers energy densities at Earth that are billions of times smaller than ordinary sunlight. Any direct causal relationship between nova radiation and SWAN's September 26th outburst would therefore require physical mechanisms that our current understanding does not support. Yet the correlation in timing is striking, demanding at least theoretical consideration of possible pathways. Could high-energy photons somehow trigger processes in cometary nuclei not captured by simple radiative heating models? Gamma rays and X-rays penetrate much deeper into solid material than visible light, potentially reaching subsurface layers where volatile compounds might lie hidden. Could such deep heating create pressure buildups that lead to explosive outgassing? The so-called energetic chain hypothesis, while highly speculative, offers a framework to explore such links. Nova radiation perturbs subsurface volatile reservoirs in comets that leads to enhanced outgassing and increased plasma production. The additional mass loading slightly alters local properties of the solar wind and heliospheric current sheet. Those changes propagate toward the Sun and, under precisely the right conditions, influence the magnetic stability of active regions nearing eruption. Each link in this hypothetical chain faces formidable obstacles. The intensity of nova radiation drops with the square of the distance, making effects at cometary distances extremely weak. Cometary outgassing depends overwhelmingly on solar heating, which dwarfs any external radiation source. Mass loading by comets is a negligible fraction of the total solar wind flux, and active region dynamics unfold according to complex magnetic systems that seem largely immune to minor external perturbations. To test such a hypothesis, we would need observational strategies capable of distinguishing genuine physical connections from the illusion of correlation produced by finely timed coincidence. So what could falsify the energetic chain idea? If SWAN's outburst began before the peak of the nova events, it would violate temporal causality. If subsequent solar flares or CMEs show no correlation with comet positions or behavior, the solar connection fails. If in situ solar wind measurements show no anomalies during periods where coupling is supposed to occur, the hypothesis loses empirical support. Historical data provide another test bed. Over the past 2 solar cycles, we've seen dozens of novae, hundreds of comet outbursts, and thousands of solar flares CMEs. If energetic chains represent a real physical process rather than rare coincidence, statistical analysis should uncover timing biases exceeding random chance. But that requires defining robust statistical tests that account for the many confounding factors. Comets erupt for many reasons: seasonal heating, structural weaknesses, collisions, random fluctuations. Solar flares follow their own internal magnetic evolution, and novae occur in binary systems independently of solar system dynamics. Human pattern-seeking biases complicate all of this. Nonetheless, dismissing the September sequence as pure coincidence might be premature. Science advances by taking intriguing correlations seriously, while applying rigorous skepticism to causal claims. The key is to produce testable predictions. If energetic chains are real, they should generate repeatable signatures as new comets approach similar configurations. The coming weeks, SWAN nearing Earth, 3I Atlas approaching perihelion, could provide a natural experiment. Do apparent correlations between remote energy sources and local solar system dynamics reflect true coupling, or the predisposition of human observers to assign meaning where none exists? The universe has posed us a puzzle. The solution will require careful observation, rigorous analysis, and intellectual honesty that balances wonder with restraint. Part 6. The Plasma Bridge Hypothesis. Deep within, plasma physics lies a possibility so elegant and so controversial that mainstream heliophysics has largely sidelined it for decades. The idea is that comets might act not merely as passive objects heated by the sun, but as transient electrodes in a vast solar system circuit capable of modulating electromagnetic flows across millions of miles. This is sometimes called the plasma bridge hypothesis. Its roots trace back to Hannes Alfvén, the Swedish physicist who laid the foundations of magnetohydrodynamics. Alfvén recognized that space is not empty but filled with charged particles and magnetic fields capable of carrying electric currents and storing electromagnetic energy across astronomical scales. In his view, the solar system resembles a gigantic electrical circuit. The sun acts as the central generator, sending charged particles and magnetic fields outward as the solar wind, while planets, asteroids, comets, and the heliosphere act as nodes or loads. Most objects in that circuit behave passively. They absorb or deflect solar wind energy without significantly altering the global current. But comets, Alfvén argued, might be different. When they outburst, suddenly producing large quantities of gas and plasma, they could temporarily change the electrical properties of their local environments, creating feedback effects that propagate through the circuit. The mechanism would exploit double layers, regions in plasma where positive and negative charges separate, creating strong electric fields that can accelerate particles and drive currents. If a comet outbursts, the ionized gas expelled might self-organize into electrical structures that interact non-linearly with the solar wind. In dusty plasma, the kind found around comets where dust grains are charged and mingle with ions and electrons, the behavior can deviate significantly from simple magnetohydrodynamics. Dusty plasmas can form self-organizing fields, generate mini-electric potentials, and respond in nonlinear ways to external forces. In principle, an outbursting comet embedded in a heliospheric current sheet might, for a short time, establish a plasma bridge linking itself to the sun or nearby structures. That bridge could influence how electrical disturbances propagate across the system. While speculative, this hypothesis is not entirely without support. Plasma double layers and localized electric structures have been studied in laboratory and space plasmas. AGU publications. However, applying it to comets raises huge challenges. The currents, fields, and densities involved are minuscule compared to solar values. Even if plasma bridges formed, their effects would be minute relative to the overwhelming scale of the solar wind. Mainstream theory would demand extremely fine tuning or resonant conditions. But plasma physics is notorious for nonlinear amplification. Tiny inputs, if applied under the right circumstances, can trigger outsized responses. Here, magnetic field lines from opposite solar poles meet and reconnect, creating zones of enhanced particle acceleration and current flow. Objects that pass through these boundaries experience abrupt changes in their electromagnetic environment, changes that can provoke dramatic reactions in their plasma tails and coma. Because SWAN's trajectory keeps it traveling very close to the ecliptic plane, its exposure to current sheet crossings and magnetic discontinuities is maximized. When the comet erupted on September 26th, it wasn't just brightening. It may have been transforming into a kind of active electrode, capable of perturbing local current flow patterns in ways that might propagate back toward the Sun. However, the evidence requirements for such plasma bridge hypotheses are daunting. A genuine electromagnetic coupling between comets and solar activity would demand repeatable correlations in particle spectra, radio emissions, and local magnetic field measurements across multiple comets and solar events. We would expect consistent timing relationships between comet outbursts and solar flares, especially when comets cross or lie near current sheet boundaries. In reality, our observational tools are limited. We lack in situ plasma measurements at SWAN's position, so we must rely on remote sensing and computational models to infer what might occur in the comet's immediate environment. Instruments like the Parker Solar Probe and other missions deliver excellent data about solar wind conditions near Earth, but extrapolating those to a comet many millions of miles away requires sophisticated modeling, and that introduces significant uncertainties. Nonetheless, there is historical precedent for dramatic comet-solar wind interactions. The 2007 encounter between Comet Encke and a CME is among the clearest examples. In that case, the CME's magnetic shock front severed Encke's ion tail, and the stereo spacecraft recorded the entire event in detail. To return search for space math, MHD modeling of that event shows how the CME's rotating interplanetary magnetic field could rotate and reconnect with the comet's tail field structure, triggering sudden disconnection, whilst turn zero search 16 orchis. But in Encke's case, the interaction was unidirectional. Solar activity disrupted the comet, not the reverse. Evidence for feedback from comets back to the Sun remains speculative, still residing largely in theory rather than observation. That said, the plasma bridge hypothesis makes specific predictions for the October convergence period. If SWAN and 3I Atlas can influence solar activity via electromagnetic coupling, we might observe correlations between their positional or activity metrics and the onset or strength of solar flares, in patterns that exceed chance radio telescopes, detecting coherent emissions tied to current flows between comet, loci and active solar regions, particle, detectors registering anomalous populations of energetic ions or electrons that trace back to cometary sources. On the flip side, the energy scales involved in solar activity vastly exceed what comets can supply. Therefore, if feedback effects exist at all, they must be extremely subtle or require precise resonance conditions. It's entirely possible that the apparent synchrony between comet outbursts and solar flares arises from coincidence amplified by human pattern recognition bias. Regardless of outcome, pursuing the hypothesis advances our understanding of electromagnetic energy flow throughout the solar system. If plasma bridges are real, then our cosmic neighborhood may be far more tightly coupled and responsive than current models suggest. A living circuit in which energy and information flow both ways between the Sun and its distant wanderers. The coming weeks will test whether this coupling is physical reality or simply an artifact of human cognition. Then, as if orchestrated, Part 7, A Historical Echo, Oumuamua and the 2017 Mexico quake. Sometimes the universe appears to choreograph events so precisely that even skeptics pause. September 2017 is one such episode, when cosmic events and terrestrial catastrophe aligned with disturbing timing. The sequence began on September 6th with an X9.3 solar flare, one of the most powerful eruptions ever recorded. The CME that followed sped toward Earth at speeds exceeding 4 million ms, triggering strong geomagnetic storms and auroras seen as far south as Alabama. 3 days later, on September 9th, the interstellar visitor Oumuamua, often spelled Oumuamua, reached perihelion at about 25 million miles from the Sun. This elongated, tumbling object had journeyed through interstellar space before being captured on a hyperbolic trajectory through our system. The cosmic drama escalated. On September 10th, exactly 24 hours after Oumuamua's closest approach, the Sun erupted again with an X8.2 flare, the second major X-class event that cycle. The back-to-back flares created sustained extreme space weather, bombarding Earth's magnetosphere with high-energy particles and electromagnetic radiation. Then, as if orchestrated, Earth itself trembled. On September 8th, coinciding almost exactly with the timeline of the solar and interstellar events, an 8.2 magnitude earthquake struck southern Mexico, Chiapas region. The quake generated tsunami warnings across the Pacific and was felt hundreds of miles away. The timing is remarkable. Major earthquake 8.0 frequency on Earth globally is about once per year. X-class solar flares occur only several times per solar cycle. Interstellar objects passing through perihelion are extraordinarily rare. The odds of all three aligning in a 4-day window are astronomically slim. Yet official science remains cautious. The U.S. Geological Survey and much of mainstream geophysics maintain there is no demonstrated causal link between space weather and earthquakes. Earthquakes are understood as releases of tectonic stress in Earth's crust, driven by plate motion and internal dynamics, independent of solar or cosmic events. Numerous statistical studies over decades have found no significant correlation between solar activity and seismicity, but alternative research groups argue otherwise. Some peer-reviewed studies propose statistical relationships between atmospheric or ionospheric anomalies and earthquake occurrence. These models invoke lithosphere-atmosphere-ionosphere coupling, suggesting that electrical charge buildup in stressed rock may propagate perturbations upward, creating electromagnetic signatures in the ionosphere. Satellites have occasionally detected unusual electromagnetic phenomena in the days preceding major quakes. Proponents speculate that intense geomagnetic activity, such as that triggered by X-class solar flares, could modulate the upper atmosphere in ways that influence seismic timing if faults were already critically stressed. The energy mismatch remains a major obstacle, but nonlinear systems sometimes show threshold effects. A small input at exactly the right moment can trigger a large output. The 2017 Mexico sequence remains a provocative natural experiment. The Tuxtla Gutierrez quake occurred in an area of known tectonic tension, Cocos Plate subducting under North America, a region already predisposed to seismic release. The question is not whether the earthquake would happen, but when. Could the intense space weather accompanying Oumuamua's perihelion and successive flares have nudged the timing just enough? To test this, scientists would require high-resolution ionospheric, magnetospheric, and seismic data from the days before the quake, cross-referenced to flare and solar wind parameters. While intriguing, the statistical and mechanistic challenges are formidable. No consensus exists to date, yet the 2017 event is at least a cautionary reminder. In a complex, nonlinear universe, coincidences that seem impossible demand scrutiny. Magnetic field lines from opposite solar poles meet and reconnect in the heliospheric current sheet, creating zones of enhanced particle acceleration and current flow. Objects traveling through these zones experience sudden shifts in their electromagnetic environment, shifts that can trigger dramatic responses in their plasma tails and coma. Because SWAN's trajectory hugs the ecliptic plane, it maximizes its exposure to current sheet crossings and magnetic discontinuities. When SWAN outburst on September 26th, it wasn't merely brightening, it may have been morphing into an active electrode, with the potential to perturb local current flows in ways that could propagate feedback toward the Sun. However, the evidential bar for such plasma bridge hypotheses is extremely high. A genuine electromagnetic coupling between comets and solar activity would require consistent correlations in particle spectra, radio emissions, and magnetic field measurements across multiple events and objects. One would expect repeatable timing patterns between cometary outbursts and solar flares, especially when comets lie near the boundaries of the current sheet. In practice, our observational tools remain limited. We have no in situ plasma measurements at SWAN's location, which forces reliance on remote sensing and modeling to infer what may be happening in its immediate environment. Missions like Parker Solar Probe and others deliver excellent data on solar wind conditions near Earth, but extrapolating those to a comet millions of miles away requires complex modeling that introduces large uncertainties. Still, Historical precedent exists for dramatic comet-solar-wind interactions. The 2007 encounter between Comet Enki and a coronal mass ejection, CME, is among the clearest examples. Stereo spacecraft observed that the CME's magnetic shock front severed Enki's ion tail. MHD simulation studies of the April 20, 2007 event reproduced how a sudden rotation of the interplanetary magnetic field, followed by further rotation, triggered tail disconnection. Art of +1. In that case, the interaction was one-way. The CME affected the comet, not the reverse. The plasma bridge hypothesis makes more ambitious predictions for the October 2025 convergence. If SWAN and 3I Atlas can influence solar activity, we might observe correlations between their positions or activity states and solar flare, onset or strength that exceed what random chance would suggest coherent radio emissions. Tracing currents between comet zones and solar active regions, particle detectors capturing anomalous energetic particle populations that trace back to cometary sources, but the solar activity energy scale dwarfs what comets can contribute. If any feedback exists, it must be extremely delicate or require resonance. The synchrony we observe between comets and flares might simply result from coincidence amplified by our pattern-seeking tendencies. Nevertheless, exploring this possibility is scientifically valuable. If plasma bridges exist, they could recast our view of the solar system as an interconnected circuit where energy and information flow both directions between the sun and its distant wanderers. Whether confirmed or falsified, the coming weeks will test whether this coupling is physical reality or a reflection of human desire for cosmic meaning. Part 7. Historical Echo, 2017. Mexico earthquake and solar events. Sometimes the universe appears to choreograph events with uncanny timing that even skeptics cannot ignore. In September 2017, a sequence occurred that intertwines cosmic activity and terrestrial disaster in ways that continue to puzzle. The sequence began on September 6th with an X9.3 solar flare, one of the most powerful ever recorded. A massive CME followed, racing toward Earth at over 4 million mph and triggering geomagnetic storms and auroras visible far from the poles. 3 days later, on September 9th, the interstellar visitor Oumuamua reached perihelion at 25 million miles from the Sun, traveling on a hyperbolic trajectory. The timing was already intriguing, but the Sun struck again on September 10th, just 24 hours later, erupting with an X8.2 flare, creating back-to-back X-class events that bathed Earth's magnetosphere in energetic particles and electromagnetic disturbances. Nestled between those cosmic blows, on September 8th, an 8.2 magnitude earthquake struck southern Mexico, Chiapas. The epicenter was near the town of Tuxtla Gutierrez, triggering tsunami warnings, and tremors felt hundreds of miles away. The alignment is startling. Major earthquakes, 8.0 magnitude, occur about once a year globally. X-class solar flares occur a few times per solar cycle. Interstellar visitors passing near the Sun are exceedingly rare. The probability of all three phenomena clustering in a 4-day span by chance is vanishingly small. Then, as if orchestrated, yet scientific institutions maintain caution. The U.S. Geological Survey, USGS, and mainstream earthquake science assert there is no proven causal link between space weather and seismic activity. Earthquakes are understood as the result of internal tectonic stresses and plate motions, largely independent of external electromagnetic events. Decades of rigorous statistical analysis show no consistent correlation between solar activity and earthquakes. However, alternative research has explored possible couplings between atmospheric and ionospheric anomalies and seismic activity. Proposed mechanisms, described in the lithosphere-atmosphere-ionosphere coupling models, suggest that electric charges may accumulate in stressed rock, produce electromagnetic signatures upward through the atmosphere, and interact with the ionosphere. Satellites have occasionally detected unusual electromagnetic emissions days before major earthquakes. Some argue that intense geomagnetic activity could modulate these upper atmospheric conditions further, potentially influencing the timing of seismic release in fault zones already nearing failure. The energy scales remain a major obstacle, but nonlinear systems sometimes respond dramatically to small inputs when near critical thresholds. The 2017 sequence is thus a provocative case study. While tectonic stress, subduction, and internal geology explain the quake's inevitability, One might ask whether space weather influenced when the rupture occurred. Testing that hypothesis requires high-time resolution ionospheric, geomagnetic, and seismic data cross-linked with solar event timing. No consensus exists. But the episode reminds us that coincidences that strain credulity deserve investigation. The results exceeded expectations. During comet sighting spring's close approach to Mars, the comet's dust and gas dramatically altered Martian atmospheric chemistry. Metallic ions were deposited throughout Mars's upper atmosphere, and ionospheric disturbances persisted for days after the encounter. The energy deposition was sufficient to heat Mars's upper atmosphere by several hundred degrees, demonstrating that comets carry enough mass and energy to measurably affect planetary systems. lasp.colorado.edu+2 AGU Publications +2. If a comet can so profoundly influence the thin atmosphere of Mars, the possibility of electromagnetic coupling with the vastly larger and magnetically active Sun becomes difficult to dismiss. These encounters reveal comets as more than passive chunks of ice and rock. They behave as dynamic, electrically active objects able to reshape their electromagnetic surroundings and influence other bodies they encounter. When embedded in the solar wind and the heliospheric current sheet, outgassing comets act as temporary plasma sources that can locally reconfigure magnetic field lines and particle flows across millions of miles. The conductive probe metaphor, while speculative, offers a helpful way to think about how comets might sample and even influence the electrical state of interplanetary space. As they traverse regions of varying magnetic field strength or polarity, their plasma production and tail morphology shift. Those changes, in turn, could influence local current flows and, in theory, propagate effects back toward more distant structures. Still, mainstream heliophysics remains appropriately cautious about claims of comet-sun feedback. The energy scales controlling solar activity dwarf what any comet can contribute. The Sun's magnetic field contains energy enough to sustain human civilization many times over. While even a large comet is a negligible perturbation when compared to stellar processes, plasma physics is notorious for nonlinear responses. Small inputs, under the right conditions, can trigger large outputs. The key, then, is identifying when and where such threshold effects might happen. Solar active regions in the corona often spend days or weeks building magnetic tension before erupting as flares or CMEs. During those build-up phases, the system may be especially sensitive. If a comet embedded in the heliospheric current sheet could influence local electromagnetic conditions, and if those influences propagate toward the Sun at near light speed, then timing becomes crucial. A small perturbation arriving just as an active region nears. Instability might trigger a premature eruption, much as a tiny tremor can set off an avalanche on a precarious slope. Testing these ideas demands rigorous observational strategy. We need coordinated measurements of comet positions, activity levels, and plasma characteristics during periods of solar flare production. We also need statistical analyses across many events to check whether apparent correlations exceed mere chance. The upcoming October convergence, SWAN approaching Earth and 3I Atlas nearing perihelion, offers exactly such an opportunity. If comet-solar electromagnetic coupling is real, this geometry should enable detectable signatures in space weather data. If no effect appears, the convergence may simply reveal normal comet behavior under standard solar wind conditions. Either result deepens scientific understanding, but one outcome might force a radical rethinking of electromagnetic relationships in the solar system. The forgotten mysteries of Enki and sighting spring remind us that nature still holds surprises beyond conventional assumptions. As October approaches, we may be poised for another chapter in this cosmic drama of plasma, fields, and invisible forces. Part 9. The Nova-Solar Coupling Hypothesis. In the celestial library of astrophysical phenomena, few events rival novae in sheer scale. When a white dwarf in a binary system accumulates enough material from its companion, it can undergo a thermonuclear runaway, erupting with a brilliance that can outshine entire galaxies and flooding nearby space with high-energy photons traveling at light speed. The two novae of September 2025, V7994 Sagittari and V11935 Centauri, were exactly such cosmic explosions. Their gamma-ray and X-ray emissions swept across the solar system, delivering high-energy flux to Earth and the inner planets in days. The fact that these arrivals coincided with SWAN's mysterious outburst and a subsequent solar flare demands investigation, even though it treads speculative ground. The skeptical case against nova. Solar coupling is strong. Photon flux from distant stellar explosions, though carrying immense total energy, is spread thin when it arrives at our solar system. Even the most powerful nova, observed over thousands of light years, delivers energy densities at Earth that are billions of times weaker than ordinary sunlight. In practical terms, the combined integrated flux of both September novae would hardly power a household light bulb for seconds. The idea that such weak input could trigger massive solar flares, events releasing more energy than all of human civilization's output, seems to violate principles of energy, balance and proportional response. Yet, in complex nonlinear systems, surprises happen. The question is not whether nova radiation contains enough energy to drive solar eruptions outright, but whether it could perturb delicate equilibria, subtly influencing the timing of events already on the verge of instability. Coronal active regions may linger near threshold states for days, fed by evolving plasma flows and magnetic stresses. During those marginal phases, a small external nudge, however weak, might advance or delay a flare that would happen anyway. Gamma rays and X-rays differ from visible light in their penetration depth. They can reach deeper into plasma and matter, potentially affecting ionization states, heating rates, or reconnection processes in ways that ordinary solar radiation does not. In theory, penetrating high-energy radiation might influence coronal dynamics in subtle ways omitted by traditional models. Some fringe proposals stretch further, suggesting that secondary particles or neutrinos from novae might interact with solar plasma, amplifying tiny perturbations into detectable effects. But neutrino interaction cross-sections are extraordinarily small. Trillions pass through the human body every second with negligible effect. The odds that far-distant nova neutrinos meaningfully influence solar dynamics in our current physics framework are effectively zero. Another possibility is that what we observe is not a true physical link, but a synchrony illusion, the human pattern recognition bias that sees meaningful connection in events that cluster in time. Solar rotation introduces our 27-day periodicities in active region evolution. The heliospheric current sheet itself has recurring structure. Cometary orbits follow predictable timing cycles. And observational biases further highlight dramatic events over mundane ones. Different independent periodic processes sometimes align by chance, producing apparent synchronization without any causal connection. To test the nova-solar coupling hypothesis rigorously, one would catalog nova explosions over decades, recording time, distance, and energy output, and compare that dataset against solar flare and CME records. Statistical cross-correlation, Monte Carlo simulations to correct for multiple comparisons, and careful accounting of selection biases would be essential. Gusts of visual memory favor dramatic coincidences, while countless non-coincidences fade into background. Only by rigorous statistical methods can one distinguish true coupling from illusions. Then, as if orchestrated, in the end, whether the nova coupling hypothesis proves real or false, tackling it drives us deeper into understanding how energy and information flow in our cosmic neighborhood. Do novae speak to our sun? Or do we impose narratives on a universe that is, by default, indifferent? Then comes the test, whether the apparent correlations in actual observations exceed what would be expected from pure chance. The interim verdict on nova-solar coupling must remain one of watchful curiosity, not confident acceptance or dismissal. The arguments against direct causation, based on energy scale mismatches, are formidable, but in complex systems, threshold effects sometimes allow small inputs to produce outsized responses under precise conditions. As we approach October's convergence, with SWAN near Earth and 3i Atlas approaching perihelion, the solar system becomes a natural laboratory. We can test whether apparent correlations between distant energetic sources and local solar activity reflect genuine physics or merely our human propensity to find patterns. The coming weeks may reveal if the September nova sequence marks the opening movement of a cosmic symphony, or serves as a reminder that, in a universe filled with billions of energetic bodies, remarkable coincidences are not only possible but inevitable. Part 10. 3i Atlas. The Enigma. the sun hidden in the glare of our star, invisible to ground-based telescopes, lies an object that challenges everything we thought we knew about interstellar visitors. 3I Atlas. Discovered on July 1, 2025, by the Asteroid Terrestrial Impact Last Alert System, ATLAS survey in Chile, this interstellar object is now among the most enigmatic and potentially consequential discoveries of the 21st century. Unlike its predecessors, the asteroid like Oumuamua or the more cometary 2I Borisov, 3I Atlas follows a hyperbolic trajectory that will bring it to perihelion around October 30 at about 1.4 astronomical units from the Sun. That places it just inside Mars's orbit at closest approach, making it the nearest interstellar visitor ever observed during its solar encounter. The geometry of 3I Atlas's orbit presents both challenges and opportunities. In September and early October, its solar elongation, its angular separation from the Sun in our sky, remains extremely low. From Earth, it appears too close to the Sun to see with conventional telescopes. Studying it thus depends on coronagraphs and space-based instrumentation capable of penetrating solar glare. But what the object lacks in Earth-based visibility, it partially compensates by proximity to Mars and Mars-orbiting spacecraft. ESA and other agencies are planning to task Mars and Jupiter missions with observing 3I Atlas during its closed solar passage, potentially giving us unprecedented insight into an interstellar object in the inner heliosphere. The predicted closest approach to Mars occurs around October 3rd, when Atlas passes within 30 million kilometers aeropion, 19 AU. This is far in human terms, but places Mars-based instruments, like orbiters and probes, within range for spectroscopic measurements, dust detection, and monitoring of any coma formation or outgassing as the body undergoes peak solar heating. Early observations already hint at differences from earlier interstellar visitors. There are suggestions that 3I Atlas might be developing a substantial coma, more pronounced than was seen for 2I Borisov during its 2019 passage. But such claims remain speculative, constrained by the difficult observing geometry and low solar elongation. One speculative but evocative idea is the hidden colossus hypothesis. If Atlas contains large amounts of hypervolatile substances, e.g., CO, N2, it might sublimate aggressively, forming a huge coma. Such a coma, extending millions of miles, could become a sizable plasma source in the inner heliosphere and influence local current flows. If so, Atlas might act as a kind of interstellar electrode, interacting with the heliospheric current sheet and possibly modulating electromagnetic structures. Previous interstellar objects were relatively inert, giving little chance to study how interstellar material interacts with our solar wind. If Atlas is more active, it might be the first opportunity to test those interactions directly. One metaphor sometimes used is the interstellar capacitor, an object carrying magnetic or electric signatures from interstellar space, entering the Sun's domain and potentially interacting in novel ways. But testing those ideas demands advanced observations. Spectroscopy could reveal volatile composition. Polarimetry could detect dust characteristics. Radio observations may catch coherent signals from plasma interactions. Yet, disentangling true physical signatures from observational artifacts is hard. The low solar elongation makes ground-based observation difficult. Space telescopes capable of glare suppression are limited in number. One key observable is non-gravitational acceleration, tiny deviations in orbital motion caused by outgassing. Previous interstellar objects exhibited measurable non-gravitational effects, confirming active behavior despite exotic origin. If 3I Atlas shows similar anomalies, that would strongly suggest volatile-driven activity and lend weight to hypotheses of electromagnetic coupling. ESA's decision to direct Mars Express, the ExoMars Trace Gas Orbiter, and potentially the Jupiter Icy Moons Explorer, JUICE, toward Atlas, is ambitious. Combined measurements during its perihelion passage might yield the first comprehensive data set on an active interstellar body in a strong solar radiation environment. With SWAN approaching Earth and Atlas nearing perihelion in simultaneous phases of high activity, this convergence offers a rare chance to compare two very different classes of objects coincidental. The observations to come promise to deepen our understanding of how solar wind, plasma, and interstellar matter interact. Part 11. Solar Cycle 25 reaches a breaking point. The Sun is awakening, and doing so with energy that's surprising many solar physicists. Solar Cycle 25, which officially began in December 2019, has consistently outperformed early predictions and is building toward what could become one of the most active solar maxima in recent decades. When the Solar Cycle 25 prediction panel published its forecast in 2019, they estimated a relatively mild cycle, peaking at a smoothed sunspot number of 115 in July 2025, plus sides 8 months. NOAA Space Weather Prediction Center +2 National Weather Service +2. Many scientists expected a cycle comparable or weaker than Cycle 24. Space +3 Wikipedia +3 Almanac However, observed solar activity has exceeded those predictions. From 2020 through 2022, sunspots, flare rates, and CME frequencies all rose faster than expected. NOAA +3 double Wikipedia +3 Helio forecast +3. Some recent forecasts now even suggest a peak sunspot number in the range of 137,164 by late 2024 or early 2025. This IDC +2 Helio forecast +2 then, as if orchestrated. It appears Solar Cycle 25 is stronger than anticipated. Some models, such as a quantile-based superposed epoch analysis, estimate a modest peak perhaps around a 130, but still within a higher than predicted band. Our sketch observational data suggest the cycle may have already peaked, or that we are very near the peak. Space +2, Space +2, NOAA, NASA, and other agencies caution that the final peak can only be confirmed after observing a consistent decline in activity. NASA Science. What does this matter for your narrative? It means that solar activity is elevated, creating a more volatile background against which comets and interstellar visitors may interact electromagnetically. In a solar environment already primed for flares and CMEs, small perturbations, if they exist, might find more fertile ground to manifest effects. So the stakes are higher. Solar Cycle 25's unexpected vigor makes the October convergence all the more compelling. As you observe SWAN's near approach, 3I Atlas's perihelion, and the Sun at a possibly sensitive state, you may be watching not just coincidence, but a grand experiment in solar, cometary, and plasma physics. The M6.4 flare on September 28th erupting from active region 4232 fits neatly into this pattern of heightened solar activity. Though M-class flares are common during solar maximum, the consistency and intensity of recent events hint that Solar Cycle 25 may be building to a crescendo rivaling some of the most memorable storms in recorded history. The Space Weather Prediction Center tracks multiple indices to monitor the Sun's electromagnetic output. One key measure is the F10.7 solar flux, a radio emission that strongly correlates with overall solar activity. It has remained elevated throughout 2024 and into 2025, indicating a persistently active Sun. Likewise, X-ray flux data from GOES satellites show a baseline increase in background flux, suggesting enhanced coronal heating across multiple active regions. Perhaps most tellingly, the rate of Earth-directed coronal mass ejections, CMEs, has increased markedly over the past year. These billion-ton clouds of magnetized plasma, when Earth-directed, can spark geomagnetic storms that disrupt satellite communications, produce spectacular auroras, and, in extreme instances, damage power grids through induced currents. Underlying this elevated activity is a complex dance between the Sun's magnetic fields and plasma flows transporting energy from its core to the surface. Active regions are areas where intense magnetic field lines emerge through the photosphere, often visible as sunspots. Over days or weeks, plasma motions twist and stress those field lines. When magnetic tension overcomes plasma confinement, reconnection occurs, releasing stored magnetic energy as flares and CMEs. The energy involved is vast. A single large solar flare can unleash more energy than 10 billion hydrogen bombs. Powerful CMEs can carry enough momentum to affect planetary magnetospheres across vast distances. What distinguishes the current cycle are several emerging patterns. longer persistence of active regions as the Sun rotates, suggesting stronger magnetic field anchoring and greater stability. The butterfly diagram, which tracks sunspot latitudes, suggests we may not have reached peak activity yet. Maximum conditions may be upcoming. Improved magnetic connectivity across the solar surface. Coronal holes and high-speed solar wind streams link distant active regions, potentially creating sympathetic flaring, where an eruption in one region triggers or destabilizes another region far away. Some researchers draw analogies to the Carrington event of 1859, the strongest geomagnetic storm in recorded human history, which caused auroras seen near the equator and even sparked telegraph disruptions. Yet important differences must be recognized. Today, our predictive systems are far more advanced. Satellites are built with radiation hardening. Power grids are monitored and protected. We get real-time alerts. The 19th century had none of that to claim we are approaching a resonance. Saturation, a state where solar activity begins to test the limits of our space weather infrastructure, would require several criteria. Sustained sequences of X-class flares alongside fast CMEs, compound geomagnetic storms, where multiple plasma clouds arrive close together. F10.7, flux levels nearing or exceeding historical solar cycle peaks. Thanks to modern systems, we can monitor this in unprecedented detail. GOES satellites track X-ray emissions. The Solar Dynamics Observatory images active region evolution. Ground radio arrays follow CME propagation, and global magnetometer networks measure Earth's magnetic response. From October 19 to 26, this monitoring network will be crucial. If the convergence of SWAN, 3I Atlas, and enhanced solar activity yields anything beyond normal variability, it should emerge in timing, intensity, or directionality that exceeds random chance. In simpler terms, if comets and solar activity truly influence each other, we may see anomalies in data that can't be written off as routine. In terms of physical risk, we could see HF radio blackouts on Earth's sunlit side, disrupting aviation and radio communications. Auroras might appear at unusually low latitudes if Earth-directed CMEs hit under favorable magnetic conditions. More serious, massive geomagnetic storms can induce currents in long conductors like power grids, potentially damaging transformers or triggering blackouts. Satellite systems may suffer from increased radiation exposure and atmospheric drag-altering orbits. Given that solar cycle 25 may already be entering a strong phase, the upcoming October convergence is more than coincidence. It becomes a natural experiment. Whether or not Comet solar electromagnetic coupling is real, the data collected will deepen our understanding of how energy and information flow through the cosmic electromagnetic network, linking the Sun to every corner of the solar system. According to these models, stress accumulation in rock formations can generate electrical charge separations that propagate upward through the atmosphere, producing detectable ionospheric disturbances hours or days before large earthquakes. In laboratory settings, experiments have shown that stressed rocks can indeed generate electrical currents and electromagnetic emissions via mechanisms like piezoelectric effects and charge separation processes. When scaled to large fault systems, these processes might produce electromagnetic signatures that satellites could detect in the ionosphere. The more controversial step in LIC, lithosphere-ionosphere coupling models, is the reverse path. Could external electromagnetic influences affect the electrical state of fault zones and thereby influence the timing of earthquakes? Proponents argue that during periods of intense geomagnetic activity, for example following strong solar storms, ionospheric current systems might couple downward and alter the electrical environment of stressed crustal rocks. The objections are formidable. Even the most powerful geomagnetic storms induce currents many orders of magnitude weaker than the mechanical stresses driving fault ruptures. However, in complex systems, threshold effects can allow a small input, applied at just the right moment and location, to trigger a large response. Still, historical analysis offers intriguing coincidences that deserve scrutiny, even if they fall short of proof. For example, the 2011 Tohoku earthquake, Japan, occurred during elevated solar activity. Though within the normal variability of solar cycle 24, the 2017 Chiapas, Mexico quake coincided almost exactly with extreme space weather during Oumuamua's perihelion passage. The 2023 Turkey-Syria earthquake sequence occurred amid a period of heightened geomagnetic activity, though again not outside typical solar cycle bounds. These examples illustrate the central challenge of LIC research, distinguishing real physical relationships from inevitable coincidences. Globally, major earthquakes, M7+, occur roughly once per week, and significant geomagnetic storms occur perhaps monthly during solar maximum. Random overlaps are statistically inevitable, so coincidence alone cannot serve as evidence for causation. If one wanted to test these ideas around your October convergence, a Bayesian statistical approach would be ideal. One would define enhanced space weather periods, e.g. KP6 for more than 24 hours, or X-class flares with Earth-directed CMEs. Then, compare the rate of magnitude 7+ earthquakes during those periods against baseline rates during quiet times. The analysis must account for clustering and seismicity, seasonal detection biases, and multiple comparison problems, since many potential correlations will be tested. When discussing earthquake space weather links, communication ethics become vital. Public safety depends on accurate risk messaging. It is tempting to cast uncertainty in dramatic terms, but scientists must carefully distinguish speculation from established fact. The correct emphasis is preparedness, not prediction. Most major earthquakes occurred during entirely normal space weather conditions. Any electromagnetic impact would only slightly modulate the timing, probability, never reliably predict. Events as the October convergence approaches, with SWAN at its closest to Earth and 3I Atlas nearing perihelion. The global seismic community will have a rare chance to test whether cosmic events and terrestrial responses share meaningful coupling or merely reflect our pattern-seeking instincts. In the coming weeks, we may learn whether electromagnetic connections extend beyond known effects, communications, power grids, into the controversial domain of seismic influence. Whichever outcome emerges, it advances our understanding of how energy and information travel between cosmic and terrestrial realms. Part 13. Mars, 3I Atlas, and the shadow alignment. While Earth-based observers struggle to detect 3I Atlas against the Sun's glare, Mars occupies a privileged vantage point. It stands with a front-row seat to one of the most remarkable interstellar encounters in recorded astronomy. The early October geometry places Mars, ideally to observe the approach of this enigmatic object as it moves toward perihelion and potentially develops a dramatic coma around October 3rd. 3I Atlas is predicted to pass within approximately 30 million kilometers or 19 astronomical units of Mars, about 80 times the distance between Earth and its moon. Though a wide berth in human terms, this proximity brings Mars-based instruments into favorable range for spectroscopic observations, dust detection, and recording any electromagnetic interactions between the interstellar visitor and the solar wind. The significance is magnified by comparison. Oumuamua remained inert during its solar passage, and 2I Borisov developed only a modest coma in 2019. If 3I Atlas exhibits more substantial activity under peak solar heating, we might finally witness how interstellar matter behaves under intense heliospheric conditions. The European Space Agency has recognized this opportunity. Multiple Mars orbiters, Mars Express, ExoMars Trace Gas Orbiter, and perhaps others, are slated to observe Atlas during its close solar passage. Mars Express carries high-resolution spectrometers that may detect composition of any emerging coma. The Trace Gas Orbiter, built to analyze atmospheric chemistry, might pick up exotic volatiles sublimating from the nucleus. Crucially, these observations occur almost simultaneously with Earth's closest approach to SWAN, October 2021. This dual convergence, two very different celestial bodies reaching their active phases, offers a rare comparative experiment in cometary and interstellar plasma behavior. Under the same solar conditions, among the testable signatures, non-gravitational accelerations of Atlas's orbit, implying active outgassing, spectral lines of hypervolatile species, CO, N2 beyond typical coma materials, morphology and polarization of any dust tail or coma, signs of electromagnetic interaction with the heliospheric current sheet. Of course, the low solar elongation of Atlas presents steep observational challenges. Ground-based telescopes struggle against solar glare. Space-based instruments with coronagraphic or occulting capabilities are limited. Still, even modest detections of ions, dust, or orbital deviations would carry outsized significance. As October advances and Atlas approaches perihelion, its convergence with SWAN's Earth flyby frames an unprecedented observational window. Whether the alignment represents deep cosmic resonance or a statistical happenstance, the data we collect will sharpen our understanding of how comets, interstellar bodies, and the Sun's plasma environment interact. The mystery hidden behind the Sun may yet unlock new insights into cosmic connectivity. The comparison promises to reveal fundamental differences in composition, structure, and behavior between solar system natives and interstellar wanderers. SWAN, formed from the same primordial materials as our Sun and planets nearly 4.6 billion years ago, should display volatile contents and dust properties consistent with hundreds of well-studied comets. Atlas, by contrast, may carry chemical signatures of an entirely different stellar environment. Even exotic materials never before sampled in our heliosphere. Theoretical possibilities emerge when we consider how a large, outgassing interstellar object might interact with the structured solar wind environment near Mars. Mars's thin atmosphere and weak intrinsic magnetic field form a complex electromagnetic boundary, where solar wind particles engage directly with atmospheric constituents. If 3I Atlas develops a substantial coma rich in ionized gases, it could locally modulate the plasma environment through which Mars travels. We can draw a useful parallel from Comet Siding Spring's 2014 encounter with Mars. When that comet approached, its coma engulfed Mars, triggering a meteor shower that deposited metallic ions in the upper atmosphere and produced ionospheric disturbances detectable for days afterward. MAVEN and other spacecraft measured that effect, and atmospheric heating of several hundred degrees was inferred. ResearchGate +3 Science Direct plus 3AdSabs +3. If 3I Atlas turns out to be a stronger object with greater volatile output, the potential effects on Mars could be even more dramatic. But 3I Atlas offers an additional dimension that Siding Spring could not. Insight into interstellar electromagnetic properties. If the object carries embedded magnetic fields from its birth environment, or if its plasma interactions differ from typical solar system materials, Mars-based observations might provide the first direct measurements of how interstellar matter integrates into heliospheric conditions. The shadow alignment aspect of this October. Convergence further complicates and enriches the scenario. Though 3I Atlas remains largely invisible from Earth owing to low solar elongation, its position places it in electromagnetic contact with the same heliospheric current sheet layers traversed by SWAN. Despite their vastly different origins, both objects may find themselves embedded in the same complex electromagnetic environment. Just as Solar Cycle 25 shows signs of intensifying, one bold question arises. Could the combined plasma output from two large active objects traveling through the same current sheet layer produce measurable perturbations propagating through the heliospheric circuit? This is speculative territory, but plasma loading and electromagnetic coupling physics suggest such interactions, though subtle, might be detectable with sensitive instrumentation. For instance, Parker Solar Probe's magnetic field and particle measurements near the Sun could provide key data to test whether the October convergence yields signatures of enhanced electromagnetic coupling among multiple objects in the solar system. Distinguishing genuine physical effects from the natural variability of space plasmas will be a central challenge. Mars-based observations will likely focus on spectroscopy to detect exotic volatile species beyond typical cometary compounds, particle dust detectors to analyze grain size, composition, and possible anomalies, measurements of non-gravitational accelerations in Atlas's orbit, indicating outgassing forces electromagnetic, signatures or anomalies in local plasma that may hint at coupling. The timing of this encounter, just days before SWAN's closest Earth approach and weeks before Atlas's perihelion, establishes a natural progression of observational opportunities. Mars acts as a reconnaissance platform, offering advanced data to inform Earth-based observers as both bodies approach peak solar heating and activity. Whether the October convergence reveals dramatic interstellar comet behavior or confirms that cosmic visitors obey predictable physical laws under solar radiation The data collected will expand our knowledge of matter and energy in the broader galactic neighborhood. Mars thus becomes a laboratory not just for planetary science, but for studying interstellar visitors passing through our star's influence. As 3I Atlas closes in on its highest solar exposure, Mars stands ready to document whatever secrets this wanderer may reveal about the universe beyond our Sun's protective domain. Part 14. The Great October Window as the calendar pages turn toward mid-October. The stage is set for perhaps the most precisely choreographed celestial convergence in recent astronomical memory. Over a critical 7-day window, the dynamics unfolding might either redefine our understanding of electromagnetic energy flows in the solar system or confirm that even the most remarkable coincidences are simply the inevitable outcomes of orbital mechanics. October 19 marks the opening of our observation window. By this date, SWAN will have been traveling nearly a month past its dramatic September 26th outburst. Any shock waves or CMEs launched from the Sun at that time would have had time to traverse the buck 40 million miles separating the Sun from SWAN's orbital path. If comet-solar electromagnetic coupling is real, this period offers the first chance to see signs of interaction. From the ground, observers with telescopes and cameras should watch for sudden changes in SWAN's tail morphology. Disconnection events, brightness surges, or structural reorganizations, hallmarks of past comet-solar wind encounters. October 21st is the mathematical center of the convergence. On this date, the new moon ensures the darkest possible sky, maximizing sensitivity to subtle changes in SWAN's tail, or Comet SWAN reaches its closest approach to Earth at 0.266 AU and 10 million miles. Atlas continues its stealthy approach toward its October 30th perihelion. Hidden behind solar glare but potentially active, that new moon timing is especially important. With lunar light removed, ground-based observers are best positioned to detect faint structural shifts in cometary features, subtle brightness changes, or anomalous tail behavior that might signify electromagnetic interactions with solar disturbances. In parallel, space weather monitoring must operate at full capacity. Several observational streams are critical. GOES satellites and geo-monitoring continuously track solar X-ray emission to catch flare events. Coronagraphs on SOHO, Stereo, and other spacecraft follow development and propagation of CMEs, noting whether any plasma clouds head toward the regions occupied by SWAN or 3I Atlas. Radio telescopes monitor for plasma burst signatures. Type 2 radio burst signal shock waves moving through the solar wind. Type 3 bursts indicate rapid electron acceleration along magnetic field lines. Coordinated radio observations might catch coherent emissions linked to current flows, bridging comet positions and solar magnetic regions. Yet this system's perspective also demands humility about the limits of pattern recognition and the danger of projecting meaning where none exists. Human consciousness excels at weaving narratives out of disparate events. The real challenge is distinguishing genuine physical relationships from correlations that emerge when complex systems independently oscillate and occasionally align. Interstellar visitors like 3I Atlas force us to expand our ideas about what kinds of objects dwell beyond our heliosphere. Each carries messages about stellar formation, galactic chemistry, and physical conditions in the interstellar medium. If Atlas contains hypervolatile ices, exotic dust, or magnetic signatures unlike anything in our solar system, astronomers may need to revisit assumptions about comet formation in different stellar environments. Still, any claim of comet-Sun coupling must be tempered by the dominance of the Sun itself. It holds 99.86% of the solar system's mass and generates magnetic fields vast enough to sculpt cosmic rays across billions of miles. Any electromagnetic feedback from comets must operate within these overwhelming gradients. Hence, this October window is not just a testing ground for hypotheses. It is a crucible for humility. Whether the cosmos responds to our theories or not, the act of testing, observing, analyzing, challenging is itself a conversation with the universe. Yet complexity theory reminds us that dominance by large-scale processes does not rule out the existence of subtle feedbacks that operate only under special conditions. In plasma physics, small instabilities can cascade into large reorganizations if threshold conditions are satisfied. The challenge is to identify when and where such thresholds might occur. If weak, transient electromagnetic coupling between comets and solar activity does exist. Its signatures would likely be buried in barely detectable timing biases across large statistical samples. Exactly the kind of pattern requiring careful, rigorous analysis to distinguish from random fluctuations. A single event, like the September sequence, will always remain ambiguous. But systematic analysis spanning many solar cycles might reveal faint correlations hinting at real physical mechanisms rather than coincidence. This possibility underscores the important role that citizen, scientists, and amateur observers can play. Professional observatories have limited time and tend to prioritize programs grounded in established theory. Speculative hypotheses, such as comet solar electromagnetic coupling, often receive little institutional support. Meanwhile, amateurs equipped with modern digital cameras, spectrometers, and automated telescopes can amass large data sets over time. Coordinated observational campaigns, especially during periods like your October convergence, might produce data sets large enough to detect subtle statistical signatures, otherwise lost in the noise of normal solar system variability. Scientific discovery is a dance between wonder and skepticism. We must remain open to the possibility that the universe hides couplings and resonances beyond current models, but demand rigorous evidence for any new claims. That tension between openness and caution is the engine of progress. As October 21st approaches, we stand at one of those rare moments when theoretical speculation meets observational opportunity. The convergence of SWAN's closest Earth approach, 3I Atlas's hidden path toward perihelion, and enhanced solar activity sets the stage for testing electromagnetic coupling hypotheses across the solar system. The beauty of this moment lies not in predetermined outcomes, but in the act of inquiry itself. Whether we observe cosmic choreography or mere cosmic coincidence, we will have learned about the electromagnetic environment that envelopes our star, our comets, and our world. The meta-pattern emerging from this investigation suggests something profound about consciousness itself. The ability to observe, analyze, and assign meaning to the dynamics of plasma, fields, and gravity is arguably one of the universe's most remarkable phenomena. Whether the October convergence reveals unexpected connections or affirms the indifference of coincidence, we participate in a deeper mapping of the networks that link humanity to a vast and often surprising cosmos. Supporting example: Mars and Comet Sighting Spring. A useful real-world precedent supports some of these speculative ideas. When Comet Sighting Spring, C 2013-A1, made a close flyby of Mars on October 19, 2014, its coma swept over Mars and interacted with the Martian upper atmosphere and ionosphere in dramatic ways. Crescendo search. MAVEN and Mars Express measurements showed that the comet deposited metallic ions, EMG, Fe+, into the Martian atmosphere between 105 and 120 km altitude. The total dust mass delivered was on the order of 82,000 kilograms, far exceeding earlier model estimates. Turn search. The cometary plasma and charged particles temporarily disturbed Mars's magnetic boundary region. In effect, the comet's influence merged with the weak Martian magnetic environment, causing chaos in the induced magnetosphere. Turn search. These observations showed rapid ionospheric variability beyond what even large CMEs had produced, indicating that cometary input can produce novel electromagnetic effects in a planetary setting. Turn search. This event illustrates that comets can, under favorable conditions, produce noticeable electromagnetic and plasma effects on planets. If so, it lends plausibility, while not proof, to speculative coupling ideas in a solar context.